Hi, everyone. I'm Stephen. I'm a postdoc at the University of Queensland, but the work I'm presenting today was from my early honours and PhD work at James Cook University back in around 2016. And for that work, I was doing kinetic Monte Carlo simulations. So one of the problems I was interested in was the work-efficient parallel prefix sum. The first question you might have is, what is a prefix sum? And it's something that I think everyone's probably come across. Essentially, it's the cumulative sum of an array. So, for example, element 3 will become the sum up to and including element 3. In particular, for a kinetic Monte Carlo algorithm, we have a bunch of event rates for the probability that some event will happen. And we choose an event with some probability that's a fraction of, or a random number that's a fraction of the sum of all event rates. And we choose the event whose cumulative sum is the first value larger than our random number. So if we had all of our event rates as 1, then if our random number were 3.5, we'd end up choosing this event here where the cumulative sum is the first one that exceeds our random number. Now, a simple implementation for that on CPU would look something like this, where we just traverse over our array and add the previous value, and we end up with our cumulative sum at the end. And then from there, it's quite simple to search. For example, a binary search, we can halve our search space each step and find a particular value we're after. And as you'd expect, we get linear scaling with that, with the number of elements. But what I haven't mentioned yet is that the data is actually on the GPU. So I wrote this Monte Carlo code from scratch and set it up to do parallel event rate calculation. So I didn't really want to be copying data from the GPU back to the CPU just to calculate which event to choose, particularly because of the overhead that incurs. So we can see here that if we include the memory copy, then we get quite a significant decrease in performance. And I'll mention here that the benchmarking platform was this here, mainly on the Tesla V100s. From there, I went looking into parallel prefix sum algorithms. And in particular, I came across the work-efficient algorithm, which essentially is based off the fact that sweeping a binary tree and performing one add operation per node gives you order n add operations in total. So it's work-efficient. And perhaps more importantly from me back then was that it was quite well documented in how to optimize this for GPU. And there's this book here, which is a little old, but still very interesting, GPU Gems 3 from NVIDIA. And in there, and I'll be describing some of the optimizations they make before going into my own. So they show that to do this work-efficient parallel prefix sum, essentially you start with an upsweep phase where you, in parallel, do adds over each 2 elements in your input vector. We then store those at a stride of 2. Then we do adds at a stride of 2, storing a stride of 4, and so on. From there, we can then do a downsweep phase where you can see here, we've only got the sum from 4 to 5. So we add in the sum from 0 to 3. And again, these adds can be done in parallel. So we're doing as much parallel work as we can. Now, for those who are somewhat familiar with writing GPU kernels, you might know that, or you might realize that this needs a bit of communication between steps down the tree. And we're limited in how many threads can communicate to the maximum block size of our GPU. So to handle very large arrays, we actually need to scan or do a prefix sum of a bunch of consecutive blocks individually. Then we can take the sum of each block and do another prefix sum over those values, then add them back to the next block. And we can do that recursively for very, very large arrays. And with that, we have a basic implementation, which looks something like this. So we can see here's a loop doing our upsweep, and then a loop doing our downsweep, which I apologize, I don't have too much time to go into today. You may notice from this code that we're limited to, at the moment, arrays of length power of 2, but we can solve that by actually making our first optimization, which essentially needs a bit of knowledge about GPU architecture. Now, the numbers on this slide are a little bit outdated, but they're still quite indicative. So from the RAM attached to the CPU, we have relatively slow transfer across through the PCI Express bus to the GPU's RAM. From there, we have faster transfer into level 2 cache, which is accessed by all of our multiprocessors. Faster again into our level 1 cache. And then we have very fast access from level 1 cache to the multiprocessor itself. Now, what's important here is we can actually divide the level 1 cache up and partition off some shared memory. And this is level 1 cache memory that is accessible to all threads within a block. So the block will context switch between sections of 32 or warps of 32. But every thread within the block can access shared memory with very high bandwidth. So with that in mind, if we look back at our algorithm, we see here that we have all these in a loop, loads from global memory, or more likely level 2 cache, and then storing back in. But we're only reading and writing to this data within a single block. So what we can do to speed things up is actually preload that data into our shared memory. Then we can loop over and do the prefix sum in the shared memory, then store it back only at the end. And that saves transactions to level 2 cache and global memory and speed things up. And from there, to handle odd size arrays, all we have to do is load in a 0 for anything beyond the end of our array. And with all that, we can see that we get quite a significant speed up over the linear algorithm, particularly for large arrays that we care about. And this is easier seen as a throughput graph. So this is the number of items processed per nanosecond. So we can see we're getting about a 20 times speed up already, but there's more we can do. So shared memory, if we look into the details, is actually split up into 32 banks, each of 32 bits. And accesses to the same bank within the same warp of 32 threads can cause a conflict and get serialized unless those accesses are to the exact same memory address. So to illustrate that, if we pretend we have a warp of 4 threads and we only have 4 shared memory banks, if each thread were to access consecutive elements in an array, so they're all in a different bank, then that all happens in parallel and world is good. If they all want to access the exact same element, that's all in the same bank, but because of the same memory address, that's also fine. But if we have threads that are trying to access different indexes of the array in the same memory bank, then those accesses get serialized, and that's where things start to slow down. Now, why does that matter for our algorithm? Well, if we have a look, for example, in the upsweep, here we're taking our sum and we're storing it into banks 1, 3, 1, and 3. So we have a two-way bank conflict already just in this small array. And then here, banks 3 and 3, and so on. And this gets worse when you have more things happening in parallel. So what we can do is actually pad out the shared memory. So after we fill up all the banks, we skip an element. And this means that now we're storing into banks 1, 3, 2, and 0. And turns out this scales very well to larger arrays as well, or more memory banks. And in code, that just looks like this. So normally we'd be accessing elements AI and BI. All we have to do is calculate a bank offset, which is that value divided by the number of banks. And then we access AI plus its bank offset to get the actual value that we want. And with that, we can again get quite a reasonable speed up. So we're now getting close to 25 times the speed. Well, there's one more thing we can do. So far, we've been doing all of this in the one block of memory, assuming that we don't have any working space. But if we do have extra memory to work with, then what we can do is, after finishing the cumulative sum of a block, we can store the total of that block into an auxiliary array, a bit of extra memory. So then when we do our secondary cumulative sum, we can be reading from contiguous memory rather than trying to do a strided access. And that means that we can have coalesced memory fetches, and that gets us a little bit more performance. At this point, we're up to date with what the GPU Gems 3 book can do, but can we do better? So as I was implementing this, I noticed that the data structure of the upsweep tree is actually already something we can search. And remember, all we care about here is choosing an event. We don't really care about the final cumulative sum. If with this data structure, if we kind of stretch it out a little bit to make it easier to look at, we see we've already got the total of the array. So we can apply our random fraction to get a random number. Then if we take the middle element of the search space and compare that to our random number, if the random number is larger, then we take this element and store it as a prefix. We then add the prefix to the middle element of our remaining search space. And again, compare that to our random number. If the random number is smaller, we would leave the prefix as is and come down here. Then we compare prefix plus this value. Or if it were larger, we add this onto the prefix, come down. This is now our middle element. So we're comparing this plus this to our random number. And then again, if this is larger than the random number, then we choose this element. If it's smaller, we choose that element. So essentially what we're doing is doing the down sweep only along our search path and leaving the rest untouched. And what that looks like in code is this, but more importantly, what it means is that firstly, we're skipping the down sweep phase, but the real big win here is that we're skipping the secondary part for large arrays where we come back and add elements to following on blocks. So that's a whole extra traversal of the array that we're avoiding. And that actually gives us almost a 2 times speed up with and without using some extra memory as scratch space. So that was really nice. And actually, I don't have time to get into the details, but there was an algorithm implemented in NVIDIA's CUDA library, which is also a single pass algorithm for doing the general prefix sum. And I only found out about this this year, but there was a white paper on it that came out about the same time as I was coming up with this. But it turns out for 64-bit data types, at least, doing this partial prefix sum actually slightly beats the CUB algorithm, which was a nice win. But with all of that in mind, it's become pretty obvious that what we really want to do is minimize our memory transactions. And that leads us to some more optimization that we can do. And this is applicable to all the algorithms. And that is when we read our input, instead of reading it directly into shared memory and then doing our cumulative sum, what we can do is first sum consecutive elements and then store them. So then we do our prefix sum over an array that's only half the length. And then when we search back, we just have to remember to do this extra step comparing back to the input array. Now, this does use more extra memory as scratch space, since we need to have a separate memory location for our output because we need to preserve the input. But by doing that, we can again get quite a significant speed up. And this could go further by doing more work on the initial load. The limiting factor there is that the more work you do in discard, the more you're going to have to redo when you do your search. To draw some conclusions, we've seen that attention to data flow under specific use cases can help reveal optimization opportunities. And in particular, if we only care about, in this case, the sum and search operation, then we can skip the downsweep phase and, more importantly, the final summing to avoid extra reads and writes. And we can avoid even more writes by pre-summing sections of our input so that we don't have to traverse back over as many items. And more generally, and I hope this is the main takeaway of this talk that maybe you can use in your own code, we've seen that optimizing memory transactions can provide significant speed up when you're processing large amounts of data. And in general, we want to avoid transactions to global memory or even level 2 cache wherever possible. We want to use coalesced memory fetches whenever we can. And we want to use shared memory when we need to do multiple accesses within the same block, to save having to read and write from global memory all the time. And with that, I'd like to thank my PhD and honours supervisors, Professor Ron White and Dr. Bronson Philippa. And I'd also like to thank Dr. Jingbo Wang and NCI for inviting me to give this talk, as well as James Cook University and the University of Queensland's Research Compute Centre, whose cluster I ran this all on. And for anyone interested, all the micro benchmarking code for all the plots in this talk are available on GitHub here. Thank you.